Welcome to the last part of week 8 of the ECE9013 course. In this part, we will be discussing the last complexity class, which is the exponential complexity class, and provide an overview. So the exponential complexity class is the worst complexity class that we can have. This often occurs when we have recursive functions where more than one recursive call for each size of the problem. One such example is the Towers of Hanoi problem. Many important problems are inherently exponential. This is unfortunate since the cost can be extremely high. This often leads us to consider approximate solutions as they may provide reasonable answers more quickly. So for example, for the Towers of Hanoi problem, to determine the time needed to solve the tower of size n, we can show here that the order of growth is actually 2 to the power n. And you can read more about what are the Towers of Hanoi. For example, if we are given a set of integers with no repeats and we want to generate the collection of all possible subsets, this is called the power set. So for example, if we have the set of integers 1, 2, 3, 4, this would generate these sets. If the order does not matter, we can generate even more sets. So if we want to generate the power set of integers from 1 to n, assume we can generate the power set of integers from 1 to n minus 1. Then all of these subsets belong to a bigger power set, and all of these subsets with n added to each of them also belongs to the bigger power set. So this gives you an idea about the multiple recursive calls that we would need in order to solve such a problem. So this is the code to generate all of these subsets. So first we have an empty subset, and then we generate the subsets with the length lesser by 1. And then we can create a list with just the last element, and then we can, for all the smaller solutions, we can add 1 with the last element, and then we can combine them to get the complete list. So assuming that the append is constant time, the time includes the time needed to solve the smaller problem plus the time needed to make a copy of all the elements in the smaller problem. But it's important to think about the size of the smaller problem. So we need to know that for a set of size k, there are 2 to the power k cases. So how can we deduce the overall complexity? Let Tn be the time needed to solve the problem of size n, and Sn denote the size of the solution. So for Tn, it's equal to the time needed to solve a problem of size n minus 1 plus the size of the solution n minus 1 plus c, where c is just a constant number of operations. Now the size of n minus 1 is 2 to the power n minus 1. So, and we can divide that further into n minus 2 and so on. So the overall time needed for n is 1 plus 2 to the power n plus n times c, which is the logarithmic addition. So to compute the power set, we need 2 to the power n number of operations. So as an overview, here are some of the most well-known complexity classes. We have the constant complexity class, logarithmic complexity class, linear complexity class, log linear complexity class, polynomial complexity class, and exponential complexity class. Here you can explore the complexity of different variations of the Fibonacci algorithm implementation. In this one, we have the order to be O of n because of the presence of this for loop. In a recursive manner, we can actually reach a case of 2 to the power n because of the fact that we are not making use of the old copies of some calculations or some values. So although the basic implementation of the Fibonacci algorithm in a recursive manner has an order to the power n, we can actually do it in a much faster way, which by storing some of the values. So as a summary, we use the big O notation to compare the efficiency of algorithms. It's basically a notation that describes the growth of the algorithm. A lower order of growth is better, which means it's more efficient. And this notation is independent of the machine or the implementation. We typically use the big O notation to describe the order of growth. It is an asymptotic notation and provides an upper bound on the worst case scenario. Here we have the order of complexity of some of the known operations for lists and dictionaries. Thank you.